Right, this is the walkthrough for the waves test that you did very recently. This is for the waves test taken on the 15th of January 2020. If you are looking at watching this thinking you're going to get the answers for a test you've got coming up, think on your test will probably be very different. However, this will give you some hints and tips as to some of the exam techniques that work rather well when you're tackling these types of tests. So these are past exam questions. So we start with question 1. A transverse progressive wave of wavelength lambda is set up on a stretched string. The graph shows the variation of displacement y with a distance x at a particular instant of time. The displacement where the distance x is lambda over 8 is called y1. So where this distance here is lambda over 8, or an eighth of the wavelength, that's going to be y1. So one of the things that works rather well here is to annotate. I know it's multiple choice and you don't have to show working. It doesn't necessarily follow that you mustn't show working, so actually showing working can sometimes help you. So you're looking for where the values of x for which this line would cross the actual graph curve of the wave. So this would be along here, and the next one would be over here. So if we think about it, well, here we've got, that's an eighth of a wavelength. That's going to be about a quarter of a wavelength, or 2/8. So that's going to be 3/8 of a wavelength. So 4/8 is a half, 5/8, 6/8 is 3/4, 7/8, 8/8 is 1 wavelength. So this will be 9 wavelengths over 8. So we look at our options. We know it's going to be 3 wavelengths over 8, so it could be that one or it could be that one. We also know it could be 9 wavelengths over 8, so it could be that one, but the only one with them both is really that one. So what we need to do is pick the one that's got them both. B is the answer. Question 2 is a Doppler question. This test does feature quite a lot of Doppler questions, I know. It is something that I think we needed a bit more practice on at the time. So we've got here, we've got the frequency of the source. Okay, they're 400 Hertz, emitted from a train's horn. The train then moves directly away from the man and sounds its horn as it has a speed of 50 meters per second. So that's the speed of the source, not the speed of the wave there. And the speed of sound is 340 meters per second, so that's v, the speed of the sound. Now this is on your data sheet. On your data sheet you will see something written a bit like this, where you see that the frequency observed is equal to the frequency of the source multiplied by the speed of the wave divided by the speed of the wave plus or minus the speed of the source. So what you have to do is think very carefully about whether it's plus or minus here. So it says here it's moving directly away, so we know the frequency of the observed frequency will be lower than the source frequency, because we know sort of the meow rule as a car goes past you. So it's lower frequency. So the denominator of this fraction is going to have to be higher, so we'd use the plus. So F0 equals FSV over V plus Vs. Okay, we then substitute in the numbers and you end up with something like 349 Hertz. Okay, but however the question asks what is the difference in the frequency. So lots of people would pick this one, but we know that that's not right. So the difference in the frequency is going to be 400 minus the 349 Hertz, which is going to be 51 Hertz. So the answer is A. Okay, I've just gone off the page, I've just realised, just show you that. So there it is. So it's the difference that you need between the emitted frequency and the observed frequency. On to question number 3. Question number 3 is a stationary wave. The stationary wave is formed on a stretched string. The diagram illustrates the string in an instant of time when the displacement of the string is at a maximum. So you've got your fixed points here, you've got your forced node here and a forced node here. You've got a node over here as well, but do we really need it? Well, not particularly. So it tells you the frequency of the wave is 250 Hertz. Point P on the string has a vertical displacement of -1 millimeter. What will be the vertical displacement of point P after a time of 5 milliseconds? So here we want to know how many oscillations 5 milliseconds is. So in order to do that, we need to find the time period. So the time period is 1 over the frequency, which comes out very neatly to be 4 milliseconds. That's not 4 meters seconds, that's 4 milliseconds, or 4 thousandths of a second. So why have I put it in milliseconds? Because this time here is 5 milliseconds. So how many waves, how many oscillations is 5 milliseconds? Well, if we think about it, what we're saying is that that's going to be 5 over 4, which is going to be 1.25, or 1 1/4 oscillations. Okay, so it's 1 1/4 oscillations. So the moment you realize that, of course, you realize that really you're just looking for what P is actually doing. So P will have 1 oscillation, so go up to the top, then back down again. Now 1/4 of an oscillation after that is the 5 millisecond point. So if we think about it, the oscillations are split into 4. 1, 2, 3, 4. So the first one, that P, is going to be here. So the amplitude, or the displacement at P, displacement of P there after 5 milliseconds is going to be 0. On to question number 4. You've got observable interference fringes. Okay, so we're not looking at infrared, we're not looking at ultraviolet. We're just looking at observable frequencies of light. It says they're produced using light from a double slit. The intensity of the light from each slit is initially the same. The intensity of light emerging from one of the slits is now reduced. How does this affect the interference pattern? So what we have to think about is what happens at a bright fringe. Well, if you've got a bright fringe, if we add together the two wave functions, if one of them has a smaller amplitude than the other, if they've got the same amplitude, and obviously when you add them together, if they're in phase, then they'd have a maximum amplitude. So that would then give you a slightly lower amplitude than before. Why? Because this one here has the intensity reduced, so the intensity is less, so it's going to be when you add the two wave functions together, the amplitude is going to be slightly lower, so it'll be a slightly dimmer bright fringe. And when it comes to dark fringes, we know that if the two waves are exactly the same intensity, they cancel each other out, but this time they're not. So we can still add together the two wave functions, but this time they're in antiphase. Oops. They're in antiphase. I'll just draw that a little bit better underneath. But this one's got a much smaller amplitude. So this one is not going to entirely cancel out that one. So what will happen again is you'll get a slightly dimmer, but still brighter than it was before. So we're looking for a dimmer maximum and a brighter minimum. So the one that says that is bright fringes become brighter. It's not that one. Bright fringes become darker. That's true. And the dark fringes become brighter. That's the one we want. Okay, so the answer was D. Number 5, monochromatic light is of a wavelength of 450 nanometers, passes through two parallel slits 0.3 millimeters apart. Bright fringes are observed on a screen 2 meters away. How far apart are the bright fringes on the screen? So on this occasion, all we really want to do is just use the very, very simple equation whereby we know that the fringe spacing is going to be big D lambda. Well, I changed symbols. I used slightly different symbols only because I find it easier to understand. So here we've got the fringe spacing. However, we know how far apart the bright fringe on the screen, so that's what we want to work out. So do we have this big distance? Here it is, 2 meters. Good. So that's 2. You've got the wavelength, 460 nanometers. So that's 450 times 10 to the minus 9 divided by the distance apart, 0.3 millimeters. Hello. Got to remember that's going to be converted to meters. So that would be 3 times 10 to the minus 4 meters. Okay, so just remember that 3 times 10 to the power minus 4 meters. So all we've got to do then is just calculate it.